Hello guys, so this video is about some properties of the bicentric polygon family, okay, and a pair of magical pedal families. We're calling them limiting pedals. It's going to become clear why. And it's joint work with Professor Pedro Reutemann out of the Federal University of Brasilia in Brasilia, Brazil, and Ronaldo Garcia out of Federal University of Goiás in Goiânia, Brazil. Okay, so let's now look at what the bicentric family is. The bicentric family is a family of polygons that we can animate here, much studied in the 19th and 18th century. And this family of polygons is simultaneously inscribed in an outer circle, an external circle with center OEXT for external, and simultaneously circumscribes an internal incircle of sorts, centered on this point here, O-int. Now this is a Poncelet family in the sense that you can see here that you have a Poncelet iteration. If you consider this as a pair of conics, you're starting from a point on the outer conic, taking a tangent to the inner one, then drawing the chord along the tangent, and then repeating the iteration along tangents until you close the polygon. Now if you can find a particular combination of circles for which, for example, 5-gon closes, by Poncelet's porism, you're guaranteed to find such a closed 5-gon by initiating the trajectory from any point in the outer circle. Okay, so this bicentric family, bicentric because it has two centers, is a Poncelet family. Okay, now a first observation we made, and we're in the process of proving it, is that, and I don't know if this is known or was known to the sages of the 19th and 18th century, or let alone the 20th century, is that this family here, though it does not have constant perimeter nor constant area, it does conserve the sum of its angle cosines. So you can see here that the sum of cosines is conserved. Now we're in the process of proving this using Jacobi elliptic functions, and it looks promising. Okay, now what this video is about is actually a really beautiful pair of derived polygons. Okay, now a classic concept in inversive geometry is that associated to any pair of circles, okay, there are 2 points that lie on the line connecting the centers of those circles, known as limiting points. So they're represented here. They've been pre-calculated, and they're L1 and L2, and they're associated with this pair here. Now, geometrically, what this means is that if I were to invert the original pair with a circle, say a unit circle centered on L1, or a unit circle centered on L2, I would get a pair of concentric circles. Let's look at that pair there. Let's move this around. So here's a first pair of concentric circles, which results from the inversion of this outer circle here with respect to this limiting point. And here's a second pair of concentric circles, which results from the inversion of this circle here with respect to the second limiting point. Okay, now this pair of concentric circles is actually immaterial to our discussion here. So what I want to do is I actually just want to focus on the fact that given a pair of circles, for example, the bicentric pair that admits this, actually this is true for any pair of circles, but we're now focusing on a pair of circles that admits an n-periodic, a Poncelet n-periodic family. Okay, so let's look at this pair here. You can calculate, and I'm going to leave a link in the description, the 2 limiting points, L1 and L2, associated with this pair. Now, the cool observation that is really at the center of this video is that now I can perform the following calculation. I'm going to drop perpendiculars from L1 onto the 5 side lines, in this case, of this bicentric polygon. Okay, so let's go ahead, and I do believe I can do this. I can draw spokes. So these are sort of spokes or perpendiculars dropped from L1 onto the sidelines of this bicentric polygon. You can see here that sometimes the foot of that perpendicular lies in the extension of a particular sideline. And I'll consider drawing a polygon, okay, that spans those 5 feet of perpendiculars. I'm going to call this polygon the pedal polygon with respect to the first limiting point. Okay? One truly surprising observation is that when you do this, the perimeter of this polygon is invariant. It's shown up here, 8.045829. A second truly magical thing is that the sum of cosines of this polygon is preserved, of the, say, limit 1 pedal polygon. Now, because we already have calculated the second limiting point, let's repeat this operation. I'm now going to drop perpendiculars from L2, the second limiting point, onto the sidelines of the original bicentric polygon. So I can draw these alternative perpendiculars dropped from L2 onto the sidelines. You can see that this first foot of the perpendicular lies at the extension of this sideline that I'm showing with the mouse here. You can see that, for example, this other perpendicular dropped here lies at the extension of this sideline here. And likewise for this one here, which lies at the extension of this one, and so forth and so on. Okay, but I can do this. I can define the pedal polygon of the bicentric with respect to L1, it's this pink polygon, or with respect to L2. And let's draw that. Here's the bicentric polygon, the pedal polygon with respect to the bicentric polygon. Let me say this again, a third time. This dark purple polygon is the pedal polygon of the bicentric with respect to perpendiculars dropped from L2 onto the sidelines. So here's a seemingly more complicated thing. It seems like it has a self-intersection, okay? But it is the doppelganger of this one in the sense that they're both pedal polygons of the bicentric with respect to either limiting point. One thing you realize, and we're in the process of proving this, is that these twins both have invariant perimeter. Okay, so here's the first perimeter that we had seen before, it's invariant, and here's the perimeter of the second pedal polygon, shown here, second pedal polygon, also invariant. You can see that these numbers do not change as the family progresses. Well, this is pretty magical. I wonder if Jacobi or Poncelet or others that studied Steiner, Fuss, Richelieu, Kerawala, many famous mathematicians who studied the bicentric family were aware that had they calculated the two limiting points with respect to those two circles and dropped perpendiculars from them onto the bicentric family, the resulting derived polygons would have invariant perimeter. Now notice that besides having invariant perimeter, the second pedal also sports invariant sum of cosines. So here's invariant sum of cosines of the second pedal. It's a positive number. Here's the invariant sum of cosines of the first pedal, minus 422. And here's the invariant sum of cosines of the bicentrics, minus 123, or 24 if you want to aptly approximate that. Now here's another interesting geometric fact. We know that the bicentrics are inscribed in a circle and circumscribe another circle. What is the locus of the vertices of the first pedal, the pink polygon? Let's draw that. That locus is this green curve, and it's actually a loopless Pascal Limaçons. And we can ask the same question about its doppelganger, this purple polygon here. What's the locus of its vertices as the bicentrics traverse the family? Let's draw that. That's another, unfortunately drawn with the wrong color here, that's another Pascal Limaçons, and this one contains a loop, and that loop loops precisely on top of L2. So let's animate the gang. You can see here that the vertices, let me stop this, vertices of this second pedal polygon, they sort of twist here, but you can see that they all stay inscribed in this orange Pascal Limaçons. And I apologize for this confusing color. It should have been something like light blue. But we can make out what the phenomenon is. Okay, so here are the two magical limiting petals, the purple with respect to L2 and the pink with respect to L1, which conserve perimeter, which conserve sum of cosines, and are inscribed in respective Pascal Limaçons. If I change, for example, let's say the distribution or the configuration of these two circles here, and I have a way to do this, I can make one Pascal Limaçons become have a smaller loop, okay, by choosing, say, a more eccentric. To see this whole family, I would have to scale this down a bit. Okay, so we can see the whole family. I would have to move this guy to the right a bit, right? And now I can see that the two Pascal Limaçons are closer to each other, but the orange one still has a loop. To see that loop, let's turn off the two magic petals, and perhaps let's turn off even the polar family. And let's zoom in a bit so we can see that loop. So we can see there, let's move this guy to the right a bit. If we zoom in, you can see that, if I manage to do that, this outer Pascal Limaçons still has a loop, the one corresponding to vertices of the second petal. Now likewise, I can make my bicentric pair be less eccentric, and I can exacerbate the loop. And we can see another phenomenon regarding loops of these Pascal Limaçons. So let's make this be, say, 1.2, and I'm going to center these guys. There you go, and I'm going to scale this down a bit. Now, you can see here that the first Pascal Limaçons, the green one, is always tangent to the outer one, the orange one, on 2 points. Let's turn off the polar family so we can just focus, and let's turn off the spokes. We can just look at the Pascal Limaçons. You can see that the loop still passes through L2, but it touches the sort of dimple of this almost flat green Pascal Limaçons over here, and it's also tangent to the same Pascal Limaçons at this point. Okay, they're all tangent to the inner circle of my polar family, which I'm going to draw again, and I'm going to animate it. You can see here that those two Limaçons are tangent to the inner circle of the polar family. And as I bring back the two petal families, I can now see that they both move along their respective Pascal Limaçons. Now let's show two more phenomena here, and we're going to be done with this video. So we started with a 5-periodic bicentric family. Let's turn off the Limaçons. I don't need the Limaçons anymore, right? So let's turn off the Limaçons, and let's just go back to our original family. So here's a possibly a 5-periodic bicentric family. We cannot quite make out the other limiting point. There it is. Let's go ahead and put both of them on the screen. 1.2. There you go. Okay. Now what happens is if instead of a 5-periodic bicentric family, I consider a 6-periodic family. So here's a 6-periodic family. Let's animate that. Okay. Now let's draw the two magic petal polygons. There they are. Are they inscribed in their respective Pascal Limaçons? Yes, they are. Let's scale this down a bit so we can see the whole system, right? And let's just bring this back here, and let's bring this back here, and I can now animate this family. Let's take the labels out so we can see the whole thing. If I manage to do that. Okay, so there it is. So here's a 6-periodic. You can see that the outer family is still inscribed in Pascal's Limaçons with a loop. and the inner one is still inscribed in Pascal's Limaçons without a loop. The inner one, I mean the limiting one, the paddle with respect to the first limiting point. Okay, now that they both conserve perimeter, let's bring the labels back up. Let's see here. So the pink family, paddle with respect to L1, conserves perimeter, does not conserve area, but conserves sum of cosines, n equals 6. The pattern with respect to limiting point 2 conserves perimeter, as before, does not conserve area, and conserves sum of cosines. Okay? Alright. But I wanted to show you guys another thing. How about n equals 4? Let's go to n equals 4. Now something magical happens here. Let's do a bicentric reset. Let's scale this guy down. Let's move this a little bit to the left, like that. And let's animate now the n equals 4 family. Let me take the label out so we can see the whole picture. There we go. Now something new happens here. While the first limiting paddle, this pink thing here, looks similar to the previous ones, it's just a regular polygon inscribed in a green Pascal Limaçons without a loop. The second limiting polygon becomes degenerate. So if you project L2 and you compute the feet of perpendiculars of L2, okay, the second limiting point, onto the sidelines of this 4 periodic bicentric family, the 4 feet of perpendiculars are going to be collinear and simultaneously inscribed in their own Pascal Limaçons. So we're in the process of proving this. We believe this can be proven with analytic geometry, but it's a pretty interesting degeneracy. Now, if you bring back up the labels, you're going to notice something about the n equals 4 case. Okay, the perimeter of this first non-degenerate pink paddle with respect to L1 is shown up here. It's still conserved, so you can see here that it is a fixed number. The perimeter of the degenerate limit 2 polygon, here it is also conserved because you can traverse its vertices in the order they are prescribed, and you're going to basically stay on this line here on this degenerate polygon, but you can still measure the perimeter, and that perimeter is also conserved. The sum of cosines of this degenerate polygon, because it's degenerate, is fixed at 4. Okay, so I have 4 angles, and the cosines of the 4 angles are all equal to 1, meaning that their angles are all equal to 0. Okay, or 180 degrees, depending on how you want to count it. Okay, so we have 4 cosines are equal to unity, and that sum is 4. But something new happens here. For this family, exceptionally, this is the only case, for the n equal 4 case, where the sum of cosines of the first paddle with respect to L1 of the bicentrics, is not conserved. So you can see here that the sum of cosines of the pink polygon, exceptionally for the n equals 4 case, is not conserved. We're in the process of proving this, and we believe that this means that there is a pole in the function that describes the sum of cosines, and therefore we cannot apply Liouville's theorem here to prove that the sum of cosines in this specific case remains constant. Okay, now let's cover one final case, the case of the n equals 3 bicentrics. So let's look at n equals 3 bicentrics. In this case is actually rather interesting, but we're gonna have to make this guy be a bit less eccentric so we can really visualize the whole system. This one's a little larger and harder to visualize, so let's do this. I'm going to turn off for now the labels so we can take a good look at the family. Here's n equals 3. Let me move this guy to the right a little bit, actually to the left, right? Let's move it to the left a little bit, let's scale it up a little bit, and let's take a good look at the n equals 3 bicentrics. Now, n equals 3 bicentrics are also known as the poristic family. This was studied in the 18th century, originally by Chapel and then Euler. This is, say, the simplest case of a bicentric family. You have triangles that have a stationary circumcircle while simultaneously having a stationary incircle. So you have these two circles here, the bicentric circles, can be properly called circumcircle and incircle of this orange bicentric family. Okay, now as I animate this family, true to the other cases, and imagine that this family has fixed circumradius and fixed inradius. So there's a formula that relates the ratio little r by big R to 1 plus the sum of cosines of a triangle. So by definition, this family here conserves its sum of cosines because little r divided by big R is conserved. So what we were seeing with the n equals 4, n equals 5, n equals 6 families, where the bicentrics also conserve their sum of cosines, it's the triangle case, the bicentric n equals 3, is a low-end manifestation of this general principle that the bicentric family conserves its sum of cosines. So if I actually were to draw, to actually report the sum of cosines, you can see here that where's the bicentric family? The sum of cosines of the bicentric family is 1.322 and is conserved. Now a couple of magical things happen here. First of all, of course, here is the first petal. Let's turn off the label so we can see this better. Here's the first petal. Let's draw the spokes that give rise to this first petal and the spokes that give rise to the purple second petal. You can see that they continue to be inscribed in a green loopless limaçon and an orange limaçon with a loop that goes through the second limiting point. Okay? Now the first thing we notice is that, as expected and as before, the perimeters of the second petal and the first petal, though different, are the same. Sorry, though different, are both invariant. I tend to make this mistake in many of my videos. When I say they're the same, I mean they are both invariant, but they are not the same value. One is reporting 7.213 for the purple one and 5.264 for the pink one. But another magical thing happens. The sum of cosines of the three displayed triangles, the bicentric, the pink, and the purple, reported here as 1.322, are all the same, meaning that the ratio of little r in radius by big R circumradius on all families is being conserved, and it's the same value. Now, I'm going to show this in another video, but the in-radius and circumradius of either the two petal polygons here, the in-radius and circumradius is not invariant, it's not conserved, but the ratio is. Okay, so that means that the sum of cosines of these three triangle families is conserved. So we can see here numerically that these three numbers are the same. Now, not shown in this video, but I'm going to show this in some other video. I'm going to actually leave a link in the description to this phenomenon, is the fact that this triangle and this triangle both have a particular triangle center that is stationary. Each one of them has their Gergonne point, or x7, stationary on the x-axis. So there's going to be a first Gergonne, not shown here, somewhere on the x-axis, and a separate second Gergonne of the purple polygon stationary somewhere on the y-axis, on the x-axis. Please make sure to check the link I'm going to leave in the description so you can see these guys with their Gergonne points. Another thing that is really interesting is that so actually if you think about the orange family, the original poristic family, there's a paper whose link I'm going to also leave in the description by Boris Odenau, 2011 paper, where he studies loci of triangle centers of the poristic family, and he shows that many triangle centers of the poristic family remain stationary over the poristics. For example, by definition, x1, the incenter is going to be stationary over here, since this family has fixed in circle, and also circumcenter x3 is going to be stationary over the family. I do not recall if over this family the Gergonne point was stationary. I'm going to Again, leave this answer in the description. But I encourage you guys to take a look at Boris Odenau's paper, where many beautiful properties are shown about the poristic family, whose perimeter, by the way, is not conserved, unlike the perimeter of these two petals. So, as a final observation, you're going to see here that the perimeter of the poristic family, the orange polygons, is variable, whereas the perimeter of these two new objects, pink and purple, magical limiting petals, is constant. So this is a set of observations that I wanted to share with you guys on this video. Let me know what you think about it. I would really appreciate some comments. And I hope to see you in the next video. Thank you very much.